Log on, tune in, find out. Another good idea from Cambridge.
On generating the assessing exact optimal design.
Thank you, Jim. Well, I would like to start by thanking the organizers for inviting me to come. And also thank them for scheduling the conference at a time when I can actually be here, which is good. If it was later in September, the students would never let me escape. I was telling a couple of people earlier that I have 215 students in experimental design this fall, all graduate students. And that doesn't count the 45 that are taking the class in Columbia by television. And it doesn't count all the online students taking the class. So I was able to escape them for a week, which was really, really nice. This is joint work with the other people that you see here. Some of this work was in Merta Rodriguez's dissertation, and she went back to Monterey Tech as a professor in engineering, but she has recently gone over to the dark side. She is now a dean. So, and she went straight from professor to dean. She didn't become an associate dean first. And by the way, at ASU, what we tell people an associate dean is a mouse in training to be a rat. So she went straight to rat. And Brad Jones was very much involved in this research. In fact, I was telling Brad earlier that his job was to answer all of the questions at the end of the talk. And he's very good at that. So maybe we'll have a chance for that. And then Connie Bohr, who's a faculty member at ASU West. And a lot of the work in this talk is based on a paper that we published in JQT in 2010. And I'm not going to talk about all of the technical details of the algorithm, because you can read those in the JQT paper a lot more intelligently than you can listen to me talk about it. I'll give you the general idea, but you can read the paper to get all of the details. As I think has been mentioned earlier today, design optimality is really one of the great paradigm shifts in experimental design, because it enables you to actually create designs that fit the problem rather than try to fit the problem into an existing design, which I guess I've viewed as one of the big failings of Taguchi, in that he had a catalog and everything had to fit into the catalog. And I think that was a big part of the problem. We don't have to do that today. And software makes this easy. There's some software packages that really do a brilliant job of this. And so one of the questions that I'm going to talk about here a bit is what optimality criteria should we use? And we've already talked a bit about the D criteria today. And of course, what we're trying to do in the D criteria is improve or maximize or optimize the precision with which individual model coefficients are estimated. We're also going to talk about the G criteria. That's sort of the main theme of the talk. And of course, in a G-optimal design, what we're trying to do is to minimize the maximum value of the scale prediction variance over the design region. So what we want to do is we want to minimize that maximum scale prediction variance. We're also going to talk about the I criteria to minimize the average prediction variance over the design region. These two criteria are sort of some of the main themes of what we're going to do. What criterion should I use? Well, my current thinking anyway is that when you're working with first order models with interaction, when you're trying to do factor screening, that the D criteria is a really nice choice, because it does focus on precision of estimation of the model coefficients. And if you're going to do screening, having really good estimates of the individual coefficients seems to me like a reasonable idea. Second order models, either sort of classic response surface models or mixture models from mixture experiments, which might not necessarily all be second order, because you can have special cubic models and other things like that in the mixture world. either the G or the I criteria comes to mind to me, because they're both criteria that are oriented around response prediction. One is kind of trying to minimize the worst case, and the other one is trying to do really well on the average. Okay, and they both seem like reasonable criteria. Design construction. We're going to mainly use a variant of coordinate exchange to do this, and this is the Meyer and Nachsheim coordinate exchange scheme from Technometrics in '95. This is a very nice, very efficient method. It doesn't require a candidate set, and it is, I think, the state of the art in terms of exchange type methods for creating designs. And with this approach, finding D-optimal designs and I-optimal designs, or designs that have very, very high efficiency with respect to those criteria, is pretty easy. Usually in just a fraction of a second or a few seconds, computer software packages will create those designs. I've used JMP, for example, to find fairly large designs using this criteria. It seems to work pretty well. What about the G criteria? Well, this is a more challenging problem. And what makes it challenging, of course, is that every time you make a change to the design, you have this ugly optimization problem to solve. You have to find the maximum prediction variance over that design space. So you have to figure out how to search over that design space and find what the maximum prediction variance is. And that can be a little bit of a challenging problem, and it can certainly increase the amount of time required to find a good design. And my experience has been, and I don't know what yours is, but my experience has been that practitioners get somewhat impatient. You know, when you tell them that, you know, it's going to take the computer 2 hours to find this experimental design, they don't like that. I don't know why. I mean, they're going to spend anywhere from a few days to weeks to a month running the bloody experiment, right? And then they're going to spend a lot of time analyzing the data and writing up the results. So why does taking a couple of hours to find the design seem so troublesome?
Because they ask you 5 minutes before.
Well, that's true. They ask you 5 minutes before they want to start. Exactly, yeah. Yeah, there's probably some good reasons for that. But that's a phenomena that's I've always found kind of curious. I remember Charles Hicks, who taught at Purdue for many years. Anybody ever seen Charles Hicks's book on experimental design? Great little book. That's when I first started teaching design of experiments at Georgia Tech centuries ago. Earth was still cooling when I did that. I used Professor Hicks's book, and he used to always tell his students that, and his students were mainly engineering and science students like mine, and he said he always told them that if you have 10 weeks to solve a problem, you should spend 8 weeks planning the experiment, 1 week running it, and 1 week analyzing the data, which I thought was darn good advice. I give the same advice to my students. But these are the same people that when you say I need 2 hours to give you the design, they throw up their hands in frustration. So this is a problem. You want to try to be efficient, and of course this is a pretty nasty combinatorial optimization problem to begin with. There are a variety of approaches that you might consider taking to this problem, and in fact there have been a lot of people that have worked on different approaches to this problem. Branch and bound methods have been suggested and used by some authors, and I think used fairly successfully. I think branch and bound methods have some potential for this problem. The problem with a lot of branch and bound methods is the size of the tree gets really big really fast, and unless you have some way to prune that tree really efficiently, it can take a long time. It can take a long time. Simulated annealing is a method that's been used to create optimal designs, and I think that's a good approach. Hasn't been used as much as it probably could be. Linda Haynes has done some work in that area. She published a JQT, or rather a Technometrics paper back about '87 or so that talks about that. And then in recent years, starting late 90s, around 2000, there's been a lot of interest in genetic algorithms and other what I would call evolutionary optimization schemes for solving these kind of problems. And genetic algorithms can work really, really well. They can work really well. You can get excellent designs. They are not necessarily the fastest type of methods in the world. Again, your success with those will depend a lot on how well you manage the algorithm design, how you go about doing the actual process of combining the genes, if you will. If you think of the genes, each gene as being a run in a candidate design, and how you combine genes from parents to form offspring, and then how you randomly permute some of those genes to put more variety in the population, sort of like human evolution. So there's been some work done on that approach, and again, it's just not computationally very efficient. And here are some of the papers. I didn't put all of them up here. There's a long list of papers where people have dealt with this problem. John Borkowski's paper is a really nice paper. I highly recommend it because he actually has a published collection of I, D, and G optimal designs of different numbers of factors and different numbers of runs, and he found all these with GAs, and it's really a very nice piece of work. I also recommend the paper by Mike Hamada, Harry Martz, and company, because that's actually the first paper that I can find on GAs where I think the authors actually did everything the way I'd like to do it. Okay, they did a really good job of that. There have been some other papers prior to that, but the authors did some sort of shortchanging of how they ran the algorithm and make it run quicker. I mean, if you leave out some of the steps, you can make it run quicker. Okay, well, I'm gonna talk about only a few specific cases. These are the cases that we actually considered in the JQT paper, and I'm not going to talk about all of these. But we only dealt with designs from 2 to 5 factors. We could have run larger designs, and in fact we did do some larger designs. And there's not much of a computing time penalty as the number of factors go up beyond 5, and the results are actually pretty similar. Okay, so in the paper we just wrote mainly about these cases, and we considered a variety of run sizes. And I remember getting one piece of criticism about this work that the person said, well, you should have considered some bigger designs, more runs, that your results might have been different if you had more runs. And I thought about that, and I said, well, just as a practical engineer, I've always had trouble talking people into doing bigger designs. They don't necessarily want to do designs with 40 and 50 runs. I always kid my students when I teach experimental design, and one of the ways I kid them is I have these what I call Montgomery's theorems of running experiments. And like the first theorem is if you want it run right, do it yourself. Those of you that have actually run experiments know what I mean. And then the other one that I use a lot is the probability of successfully completing an experiment is inversely proportional to the number of runs. The bigger it is, the more likely that disaster will strike. And so we didn't look at big, huge designs with 40, 50 runs. We looked at designs that I think are pretty typical of what people would want to run in practice. Now, in the paper, and I'll show you this in just a bit, we reported the best designs that we could find by the DI and G criteria. The D and I designs were created using JUMP. JUMP's exchange algorithm works really well. The G optimal designs were created using, of course, the G criteria and an optimization algorithm called Brent's method that turns out to be extremely efficient. Brent's method is a one-dimensional search algorithm, and we used it for doing two things. Every time we changed a coordinate in the coordinate exchange procedure, we used Brent's method to calculate the coordinate change. Okay, so we had a really efficient way to figure out how to change the coordinate. And then we also used Brent's method to find the maximum prediction variance in the design space. And because it's a one-dimensional scheme, when we did that, we restarted it like 100 times, okay, to make sure that what we actually found was the actual point where the prediction variance was maximized. So that was all programmed up in a jump script, and we ran this in jump 7. The jump script that did this is available if you actually want it. We'd be glad to get it to you. Myrta currently has custody of it, and unless her dean duties have caused her to lose sight of everything else, she could probably get this for me without any trouble. We used a variety of starting designs, or parents, as the GE people would call them. And we sometimes started with D-optimal designs or I-optimal designs or random designs. And sometimes we would start with a specific design just to see what happened. All of our designs are on cubes. Okay, so for example, a starting design might be something like a face-centered cube design. Okay, so those are the sort of the ground rules of the situation. And it turns out that this algorithm is actually incredibly efficient. The execution time for all the problems that I showed you here is in just a few seconds. Okay, it's very, very fast. It's competitive with any of the algorithms that you would use for finding a D-optimal design or an I-optimal design. And it does appear to be pretty scalable. As you increase the number of factors or increase the number of runs, there's no massive exponential increase in the amount of computing time. This is kind of encouraging. So this is something that perhaps could be implemented in commercial software if you were interested in doing it. I'm just not even going to say anything about this. This is to check your vision. It's a whole bunch of efficiencies, and you know you don't want to look at this anyway. It's in the JQT paper. The print's slightly larger, but it's not interesting. As I mentioned, we found designs that were identical to published G-optimal designs. The 2 and 3 factor cases, there are published designs. If you look at John Borkowski's paper, he's got them. And we found some cases where we actually beat some published designs. K equal to 4, n equal 15, k equal 5, n equal 21. We would actually do a little better than the published designs. And then there were some cases where there were no published designs, and we didn't have anything to compare with. So we just had to look at the G efficiency, and the G efficiencies were either 100% or they were like 99 point something percent. So we feel pretty sure that we found good designs. The reason I didn't focus on that eye chart very much is because I think looking at efficiencies is very misleading. There are things going on in the design space that are very different at different locations. And efficiencies don't necessarily tell you all of that. Here's an example. The graph on the left is a variance dispersion graph, and we're comparing 3 designs. We're looking at a hexagon and a central composite design. The CCD has 1 center run, and then the other CCD has 3 center runs, and then of course the standard hexagon design. And of course, all 3 of these designs are rotatable for the second order model. Now here we're looking at designs on spheres. Okay, so they're rotatable for the second order model. And if you look at these VDGs, you would see with just a little bit of study that the efficiency, the G efficiency of the central composite design with 3 center runs and the hexagon are just about identical. They're just about identical. If you look at the graph at the left end for the hexagon, you'll notice that it's just a little bit above that 100% G efficiency line, and then of course at the far end the CCD is just above that, and it turns out that about 86% is the G efficiency for both of these designs, very close to 86% efficiency. But look at the performance. Look at the prediction variance performance over the design reads. It's very different. It's very different. the CCD predicts much better near the center of the region than does the hexagon. And in fact, if you actually use a fraction of design space plot to compare these designs, and that's the picture on the right, you'd notice that the central composite design of 3 center runs is uniformly better than either of these designs, because if you pick a particular value of scale prediction variance and read over and drop down to the bottom, for that particular value of SPD, the CCD with 3 center runs has the largest fraction of design space at or below that point. Wow. Now, here's what we actually did that I think is so interesting. Okay, Jeff says I have 5 minutes left, so I'll show you the interesting part of this talk. Okay, what we did is we compared these G-optimal designs that we found to D and I optimal designs, and we did it with this variance ratio FDS plot. So what we did is to calculate this quantity is for a given design point, you find the prediction variance for design I, and you compare that to the prediction variance at the same point for whatever reference design you want. And we compared D to G and I to G in these 2 variance ratio plots. The way this works is if the variance ratio is less than 1, the reference design predicts worse than design I. And if variance ratio is greater than 1, then the opposite is true. The reference design is better. Okay. So we're going to compare D to G and I to G, and there's a horizontal reference line at unity. And here's one of the plots. K equal 2, N equal to 6. And the first thing you see is that the I optimal design, which is the dotted curve, outperforms the D optimal design, which is the dashed curve. They're both being compared relative to the G optimal design. And the key thing here is that I optimal design outperforms the G optimal design over about 2/3 of the design space. Its prediction variance is lower. Very interesting. Here's another case, K equal 3, N equal to 15. Both the D and the I optimal designs have similar G efficiencies. The I optimal design outperforms the D optimal design almost everywhere, and the I optimal design outperforms the G optimal design over more than 90% of the design space. Gee. So you're going to all this trouble to create this design, this G optimal design, and the only thing it gives you is protection at the far end of the region. Huh. And here's some other cases. In fact, the picture on the right is the worst case. Brad once criticized me for showing that picture. He said, you showed him the worst case. Here the performance, once you get to about 50% of the design space, the G-optimal design is a little better. Here's a comparison to standard designs. This is 5 factors, 21 runs. The dashed line is a Hope design. And the new generated G-optimal design is the solid line. And you can see that you get a very small improvement in G efficiency with the G-optimal design. But the performance of the Hope design is much better over almost all the design space. So the conclusion is that maximum prediction variance for these I-optimal designs is always worse than the maximum prediction variance for the G-optimal design. Are we surprised? No, because that's how the G-optimal design is created. But the I-optimal designs have smaller prediction variance in most cases over a large part of the design space. For more than 60% of the cases we looked at, and I showed you the cases earlier, the prediction variance for the I-optimal design is less than the prediction variance for the G-optimal design over, well, at least 85% of the design space. Pretty interesting. So we can create these designs in seconds in many cases, but they're not very competitive. Oops. They're not very competitive with respect to prediction. Boy, I bet that's really going to impact that sound, isn't it, Jeff? That's better than the phone going off.
I thought you were just trying to do something to check your attention.
Well, what it'll do is that all the people watching the tape, they'll wake up. What was that? Have I missed something important? Well, basically, the G-optimal designs, in my view, don't turn out to be terribly competitive with respect to prediction variance over a big portion of the design space. And, you know, that's kind of a big price to pay for getting protection against the worst case, which may typically be at the boundary of the region. And when you put a central composite design or second order response surface design anyway, when you plop it down on the design space, you generally tend to center it at the point where you think is most likely where you're going to make predictions. You hope you're not making them out at the origin. So at the end of the long-winded end of this is it really worth it to create these G-optimal designs? I'm not sure. I said probably not, and you know, maybe I shouldn't say probably. Maybe I should say most of the time, probably not, unless you know that you really want to make predictions in a certain region. Then it might be worth doing it. But I used to be a big fan of this criteria, and my interest is waning because I've actually had a chance to see what they look like. Now, I have some students who have created designs using G-like criteria for other more complex problems, robust parameter design problems and things like that, mixture process type problems. We've not gone back and really studied those designs this way, and I intend to do that, and I may be even more hostile about these things later. But right now, even though we can create these things, I'm not sure I would really recommend that you do it. One way, you give me 1 minute, Jeff, 30 seconds. Okay. Could I somehow make the I-optimal designs better? And I think there's two ways that you can do that. Brad suggested one of these, which I thought was a great idea. You remember the I criteria has this matrix of region moments times this model matrix thing. Well, maybe we could expand the region so far as calculation of the region moments is concerned, and that would penalize you out near the boundary. So that's possibility one. Possibility two is to actually take the I criteria and put a weight function in the objective function where we put a heavier weight out near the boundary, some sort of function that does this as you go toward the boundary. That might make the I-optimal designs look better out near the region, boundary of the region, but probably at some suffering of what goes on in the middle. So I haven't explored either of these yet because I haven't found a PhD student that wants to think about this. They're so discouraged from the current results that they don't want to do anything with this. But I think that's some things that we could do to make things better. Sorry, Jeff, I didn't mean to run over. But I'm done. Thank you very much. I appreciate your attention. And once again, I really thank the organizers for having me here. Steve Gilmore in particular, who emailed me and said, please come. So I really appreciate that. Thank you, Jeff.
A question and comment?
Doug, it's not a question, it's an observation. I've certainly worked with groups of engineers whose first question, after I generated a I-optimal design in your terms, I usually call them V-optimal, but their first question has usually been, show me a plot of the prediction variance and tell me what's the worst case. That's that was reality for the.
I know, and the nice thing about these variance ratio FDS plots is you can show them what a overemphasis on the worst case is costing you. You know, because it means you're giving up a lot over a big portion of the design space to buy insurance against the worst case.
Of course, the next thing I try and say to them is that they should be interested in bias as well as.
Yeah, right. Another problem I didn't even talk about, but you're right. That's certainly an issue. That's certainly an issue. In fact, there's a version of these VDGs that deals with both bias and variance. It was some work from Jeff Niving's PhD dissertation that was published in Technometrics about 88 or 89. And I've always had that laying around on my desk as something to play with, but never done it. Never done it.
Other comments or questions?
I think the two criteria are very differently motivated. By assuming the I optimality and you're using a uniform weight, that says a lot what you are.
Yeah,
you know.
It says you don't know anything about where you want to make predictions.
Right, whereas the maximum one is a bit different. The target is different thing, and of course it could be different. Not only that, if there are heteroscedastic cities where you have different variances at different points, then
We didn't even think
then
about
it becomes really unpredictable, and maybe the G-optimal design may have a more
Yeah, and that's of course a much more complicated
Yeah.
problem when you start looking at the prediction variance the variance of the observations being different on the design space. But yeah, that's a very good point. I've wondered whether some sort of combined criteria might be worth looking at. I haven't done that
I'll
either.
talk about that tomorrow.
Very good.
I think we should keep the time and move on to the second speaker. During the break, there'll be a lot of time for discussions. So the second speaker is Dr. Tirthanga Das Gupta.